Okay, I have several people that have requested some information about number 20, and I'm not surprised. Don't feel bad if that problem was hard. This is a tricky problem for you where you're at and your skill set. So here is my solution. Particle starts from rest, that's an important word. It accelerates, that's an important word. As shown in figure 2.20, determine the speed, that's an important word. At 10 seconds, that's an important time, at 20 seconds. And the distance traveled, that's important, and during the first 20 seconds. All right, so what do we know? We know that the particle started at rest. So at t equals 0, the velocity was 0 meters per second. Okay, that is a very important thing. Every time you see it rest, that's important. All right, we also know that the acceleration during those first 10 seconds was equal to 2 meters per second squared. I got that off my graph. And they want to know the speed at 10 seconds. Now, speed and velocity are related to one another. They're essentially the same thing. The speed is the instantaneous speed is the magnitude of the instantaneous velocity. Okay, and since this is an instantaneous velocity that they're talking about at 10 seconds, what is the speed? If I find the velocity at 10 seconds, I can determine the speed. So I have an equation that relates acceleration to velocity. Change in velocity is change in time. V final minus V initial over T final minus T initial. Well, what was the initial velocity during those first 10 seconds? It was 0. What is the final velocity? That's actually what we're looking for. I don't know the answer to that. T final 10, T initial 0. What was the acceleration during that time? Based on the graph, 2 meters per second squared. Use the equation to solve for V final, which is the velocity at 10 seconds. And I find that 2 equals V final minus 0 over 10 minus 0. I will solve for V final, cancel all my units, and I will find that it is equal to 20 meters per second. So what's the speed? Well, the speed is equal to the magnitude or the absolute value of the velocity. And since it's a positive 20, I would take the absolute value of it. I find that it's still a positive 20 meters per second. Now let's assume that you solved that equation and you found it to be negative 20 meters per second for velocity. That's okay. That means it's just moving to the left. And so what's the speed? 20 meters per second, okay? It's the magnitude of the velocity. So that is the speed at 10 seconds. Now the next question is, what is the speed at 20 seconds? All right, I'm gonna go look up here and I go, I have this other section that I know some acceleration data about, okay? We'll talk about this acceleration data, which is equal to 0. This was equal to 2. This is equal to -3. And so I know that the acceleration is equal to change in velocity over change in time, V final, V initial, T final minus T initial. What is V final? We're looking for the velocity final. What is V initial? I happen to know it's 20 meters per second. I'll explain how I knew that in just a minute. T final was 20 seconds. T initial was 15 seconds. And the acceleration during that time was -3 meters per second squared. So how did I know that the initial velocity at this 15 seconds was 20 meters per second? Well, what was happening during this period? Was the acceleration 0? It was. So if I'm not accelerating, that means I'm not speeding up and I'm not slowing down. My velocity has to remain the same. So the velocity at 10 seconds you found to be 20 meters per second did not change between 10 and 15 seconds. And I can actually prove that to you. I can tell you that acceleration, which was 0, was equal to V final minus what was the velocity at 10 seconds? 20 over 15 minus 10. Solve for V final, you'll find it to be 20 meters per second. So it didn't change because acceleration was 0. So that's how I knew that the velocity initial at that 15 seconds was 20 meters per second. Now I can solve that equation. -3 is equal to the final velocity at 20 seconds, which is what we're trying to find, minus 20 over 20 seconds minus 15, and we find the velocity final to be 5 meters per second. Now, what is the speed? Oh, gosh. What is the speed? The speed is the absolute value of that velocity, and it is going to be 5 meters per second. Okay, so that is the speed at 20 seconds. Now, your skill sets right now, what you have in your wheelhouse, your toolbox, to solve B, the only way that you have in your toolbox to solve it is to draw a velocity versus time curve for that trip. Okay, where did it start? It started at 0. What was the velocity at 10 seconds? It was 20 meters per second. Okay, you solved for that. How did I know that line was linear? Because look at the acceleration. Acceleration's constant too. The slope of this curve is equal to 2 meters per second squared. What does the velocity versus time curve now look like between 10 and 15? Well, the slope has to be 0. How did I know that? Because look at the acceleration between 10 and 15. It's a 0. Then between 15 and 20, it decreases, but it decreases to 5. Okay, we'll call that 5. Okay. All right. What is the value of that slope? That slope is equal to minus 3 meters per second squared because of the acceleration graph between 15 and 20 seconds. Now, how do I know what the distance is? You learned in the lecture that if you had a velocity versus time curve and you want to know the displacement, you can determine it by the area under the curve bound between the curve and the horizontal axis. So I need to calculate this area. So I'm going to draw some shapes. I have this triangle, I have this rectangle, and then I'm going to take this shape and break it into 2 parts, a triangle and a rectangle. I'm going to call this area 1, area 2, area 3, area 4. And I'm going to calculate, and we happen to know that is 5 meters, this dot right here. The last velocity that we found at 20 seconds was 5 meters per second. So we know everything we need to know to calculate the areas of those shapes. Okay. So this is B, and the areas are, I'll let you kind of 10 seconds times the height plus 5 seconds times the base, sorry, base times height, plus the next triangle, which is 5 seconds times 15 meters per second, plus the next little teeny rectangle, which was 5 times run out of space, so my units are getting, that's a 5. Okay, so I have 100 meters plus 100 meters plus 37.5 meters plus 25 meters. So I add all these up. And notice they're all above the horizontal axis, so it's all a positive displacement. If I had area underneath that horizontal axis, I would actually have some negative displacement, okay? So this total displacement is 262.5 meters. Now that is delta x, the displacement. So the distance traveled happened to be the same in this case because it went in a straight line. We're not curving all over the place, okay? That is, again, it's going to get easier to calculate that in the future within the next couple weeks, but you just don't currently have tools yet to do that. Okay, so I'm going to do the next 2. You can skip, you can speed up. The certain car is capable of accelerating at a rate of 0.6 meters per second squared. How long? That's an important word. Does it take for the car to go from a speed of 55 miles per hour to a speed of 60 miles per hour? So let's write down what we know. This is acceleration. This is the initial velocity. This is the final velocity. There's what they're asking for. And so I have acceleration equals 0.6 meters per second squared. I know the initial velocity is equal to 55 miles per hour. I know that final velocity is 60 miles per hour, and they want to know how much time. First thing I have to do is convert, and I looked up and found that 1 mile per hour is equal to 0.447 meters per second. If you're ever needing to have something like that as far as conversion factor, you'll be given it. The ones that you won't be given are going from meters to centimeters, kilometers to meters. You need to know your SI conversions by heart. Okay, so 1 mile per hour is equal to 0.447 meters per second. And I know the order of which to put those based on the fact that I need all of those to cancel, and I get an answer of 24.585 meters per second. Same thing, 1 mile per hour equals 0.447 meters per second, and that equals 26.82 meters per second. And then I use my equation, acceleration, change of velocity equals change in time. And so I am trying to see, okay, so 0.6 is equal to 26.82 minus 24.585. This is all over time. I will find time to be equal to 3.725 seconds. Correct sig figs. If I was in AP chemistry, this is 2, this is 2. I'm sorry, that is 1, and that is 2. My smallest number of sig figs is 1, so in sig figs, I would have 4 seconds. Okay? All right. Number 24, it's actually what I did in the lecture. So I need to know average acceleration between 0 to 5 seconds, 5 to 15 seconds, 0 to 20 seconds. So I'm going to solve that equation for each interval. I find the first interval, I will get the initial velocity is equal to -8 minus the final velocity -8 over that time interval, 5 minus 0, that will be equal to 0 meters per second squared. The next time interval, 8 minus a -8 over 15 minus a 5 equals 1.6 meters per second squared. The next time interval, I get 8 minus a -8 over 20 minus 0, I find the acceleration to be 0.8 meters per second squared. Those are my 3 answers for the individual time intervals. Okay, next, I want to know the instantaneous acceleration at 2 seconds, 10 seconds, 18 seconds. All right, got to go find the tangent line. Let's go look at those. Let's go mark where 2, 10, and 18 are on this graph. So I go over here, I find 2, I put a dot on it. I go find 10, I put a dot on it. I go find 18, and I put a dot on it. Now let's look at 2 seconds. All right, notice that it's linear. The slope across that whole portion of that line is constant. So even if I were to come in and say, oh, I'm going to draw a tangent line, which is what I need to find instantaneous velocity or instantaneous acceleration, that slope is the same everywhere. That happens to be 0. So A equals 0. I have no acceleration. Okay, the slope of that whole entire line, no matter what, anywhere on that, I have the instantaneous acceleration at 1 second at 0. Instantaneous acceleration at 2 seconds is equal to 0. The instantaneous acceleration at 1.2 seconds is equal to 0. The instantaneous acceleration at 1.254 seconds is equal to 0. That entire section has an instantaneous acceleration of 0 because it's constant throughout that time. So at 10 seconds, don't tell me the acceleration is 0. What does this graph tell me? This is velocity. A lot of people are going to start getting confused between the velocity curves and the acceleration curves. That's common. That's common. Let's stay focused on what I've got to find the slope. The the slope of the tangent line at 10 seconds. Well, if I draw a tangent line, it's essentially parallel. Anywhere on that section of curve, that acceleration is exactly the same thing, which I believe we found to be 1.6 meters per second squared. Okay, so that was the acceleration at 10 seconds is 1.6. And notice it's positive, right? Okay, that entire time it's positive. Okay. All right, at 18 seconds, what's the slope of this line during that whole entire portion? 0. Acceleration is equal to 0. Acceleration is equal to 0 at 18 seconds, 19 seconds, 18.4 seconds, because the tangent line is parallel to that entire line, okay? There essentially isn't a tangent line. It essentially is the line itself. All right, I hope that explains it. Message me if you have any questions, and this will get easier. This is how we're going to learn. We're going to learn by doing problems. Have a great day. Hang in there, guys.